Okay, let's talk about operating systems now. It's Friday.
Yeah.
All right. Who's excited about Friday?
I am.
Really? Wow. Nobody? Okay. Well, I don't know what your weekend's going to be like. I'm not excited about Friday first. So today we're going to start a couple of lectures on virtualization. So virtualization is I don't know. It's sort of like you guys are, you spent all semester trapped inside the matrix, right? Like you guys thought that when you were writing Java code, you were trapped inside the matrix, and then I showed you the light here, and now you know about operating systems, like what the real world is like, right? But it turns out that you can actually, the matrix that you're got out of is itself potentially just another shell, right? And so there's a whole nother level, and this stuff gets really bizarre, right? And also pretty cool. But today we'll start talking a little bit about full virtualization, and I'll try to convince you why this is a good idea, right? Why would we want to do this, right? Because it is complicated. And so before we sort of start drowning in the details of how some of this stuff works, why, right? I have operating systems, right? Operating systems provide all these nice features. Why would I actually want to virtualize things? Let's see. I can't remember how this thing up. Oh, if I plugged it in, that would help. All right. So I think you guys have like 3 weeks left for assignment 3. Is that it? Yeah. All right. So keep cranking. Don't have anything else to say. The other thing is, so we're going to have a couple of extra lectures at the end of the semester. I will post on Piazza at some point. I'm open to suggestions for what people want to hear about. If you guys want to do a couple of sort of special topics lectures, if there's things that you guys find interesting. Alternatively, the other thing I can do that I thought might be fun, but my definition of fun is sometimes not the same as yours maybe, would be to do some lectures on sort of classic systems papers, right? So I could give you guys, for example, the paper about RAID, right? Which is a really neat one. How many people have read that paper? Ah, okay. That's a good paper. I mean, RAID is a real thing. So, unlike many academic research papers, this one came true. So that's a cool paper to read. And there's a couple of other pretty neat classic systems papers that we could look at, right? So I would assign those, and then we could sort of talk about them in class, and I could sort of walk you through them a little bit. But anyway, I'll post on Piazza and see what you guys want to do, right? We will have class. Yeah, enough.
Will those be on the test?
Will those be on the test? So, yeah, I mean, if we cover it in lecture, it's fair game, right? The other thing I would caution you, though, is I am fond of pulling, if you've looked at the past couple years' exams, I am fond of creating exam questions around recent research in computer operating systems. So everybody, when you leave today, just run out and grab the proceedings from SOSP last year and read all the papers, right? And maybe you'll be ready for one of the long answer exam questions. I'm just kidding. I don't know if there's anything interesting, but I have some things in mind already. So, but yeah, anything we cover in class will be fair game for the exam. But we're not going to go into deep details about these things. It's just there's some interesting system design principles that come up in stuff like RAID and NFS and some other things that are a little crufty, but they're classics. They're chestnuts of the computer systems literature. All right. So, but we'll talk about that on Piazza. Any questions about performance analysis and improvement from the last couple days of materials? Okay, so what were the steps, right? This could be on the exam, right? How do you improve the performance of a computer system? What is the first thing to do? Yeah, Matt.
Measure your system.
You have to measure the system, right? And this can depend on what is your system. So really the first thing is probably choose a system. Right? Choose something that you're going to do. Are you going to model it? Are you going to simulate it? Are you going to run the real thing? Measure it. Measure something about it. What do you measure? What's the next step? Yeah. Analyze the results, right? So measure your system doing something useful. Analyze the results, look at the data. Now what do you do? Yeah. Improve. Yeah, I like that. Pretty much improve the slow parts, right? Focus on the parts of the system that are the problem and improve them using whatever means are at your disposal, right? identify the right part of the system to work on, make it faster, right? We had an important principle at work when we looked at performance improvement. What are a couple of different ways of stating Amdahl's law? You guys should, as computer systems, as computer programmers, you guys need to develop a deep, intuitive understanding of Amdahl's law. So what's one deep, intuitive understanding of Amdahl's law, Adam?
The more time you put into improving something, the less likely it is to bottleneck the system.
Yeah, I like that. That's like the dark underbelly of Amdahl's law, right? What's the silver lining? Yeah.
I wouldn't call it the silver lining, but the area of improvement is always impeded by the area of unchanged.
Right. The performance of the improvements you are going to make to the system are always bottlenecked by the improvements you're not going to make to the system, right? And so if you decide to pick a part of the system to work on that's only contributing 0.1% of the slowdown, then the most you're going to get is 0.1% of the slowdown, right? So that's designed to encourage you to pick the parts of the system. And this is, again, something that is probably the most counterintuitive formulation, right? Don't pick the part of the system to work on that looks the ugliest, the part that you wrote in the middle of the night, right? Or after one too many beers, or while under emotional duress, right? Don't pick that part unless you know that part is the bottleneck. Pick the part that's actually hurting you. And yes, the more you work on one part of the system, the less likely it is the problem, all right? If you only take Amdahl's law away from those two lectures, then I will feel like they have been successful. So any other questions about performance improvement? Yeah, Adam.
Are you still going to go over like the correct way to get good statistics?
No. But partly because I don't know a correct way to get good statistics, right? I mean, that's very problem specific. Right? How many people know how to collect statistics from your OS 161 simulator? Really? Oh man, come on! I know at least a couple of you. Yeah, no one's run Stat 161.
Oh, I didn't know that.
Yeah. Oh yeah, you guys should try that sometime. It's very helpful for identifying deadlock in particular, actually. So if your current method of identifying deadlock is waiting for 5 minutes for the system to do something, then I have a better way. So yeah, I mean the System 161 simulator actually, because it's a simulator, it's pretty lightweight, has the potential to generate a lot of information about what the system is doing. In fact, I'm pretty sure you can. I remember one night when I was teaching this class at Harvard, I was trying to help some student, and we got so desperate. There's a way to actually force the simulator to output every instruction it's executing into a file, right? That file gets big. And so we were pouring through this. And of course, as all of these good debugging sessions end, what turned out was that something the student had told us he was certain of was not true, right? And so anyway, but it does have that capability. So I mean, that's about the most detailed information about a system that you'll possibly be able to get, right? Every instruction as it's executing. It's kind of cool to look at in a way. It's pretty neat. All right, so let's start talking about virtualization. So up until now in this class, we've been focusing on how operating systems run on real hardware, right? How operating systems manage real physical devices, right? And to some degree, the goal here has been getting the operating system to provide a certain degree of isolation between applications, right? And to manage real hardware resources. But at this point in time, I don't know, this is a great at this point in time, sounds very, I'm actually wondering what percentage of operating systems now actually run on real physical hardware, right? A lot of the operating system instances out there in the world, my guess is a growing fraction run inside what's called a virtual machine. How many people have used a virtual machine before? Okay, good. At least you know what VirtualBox is, right? It's a suggestive name, right? So a virtual machine is sort of we call it a VM, and a virtual machine is designed to express the fact that it is not a real machine, right? I mean, when you run up VirtualBox is using your hardware to create a virtual machine. The piece of software that we use So we distinguish between the virtual machine, which is sort of the abstraction, and a virtual machine monitor, which is a piece of code that provides that abstraction. You know, people talk about VMware being a virtual machine. Fine, right? I mean, you can sort of use those terms interchangeably. What it's actually doing is implementing a virtual machine for the operating system that runs inside of it, right? And now, because things, you know, we're introducing this whole new universe, we need some more terminology, right? So we refer to the operating system that runs inside the virtual machine as the guest, right? And we refer to the operating system that runs outside of the virtual machine as the host, right? So the guest operating system runs inside the virtual machine on virtualized hardware. The host operating system provides the host runs the virtual machine monitor, right, which provides the VM environment, right? So your laptop would be the host OS, and the copy of Ubuntu Linux that's running in your VirtualBox is the guest, right? That's kind of intuitive terminology. So virtual machines differ from physical machines, right? Clearly, but in some important ways, right? So the first thing is you can't provide. So operating systems are used to having privileged access to underlying hardware and exclusive access to underlying hardware, right? So virtual machines break this guarantee or this normality, right? You do not provide the guest OS with exclusive access, right? Your VirtualBox is probably configured to provide Ubuntu with access to a certain amount of the memory on your machine, right? Not all of it. You also cannot, and these two things kind of go together, but I can't allow the guest operating system to run in fully privileged mode. Why not? What would happen if the VMM allowed the guest operating system to run with the full privileges it's used to? Yeah.
The host OS might not provide that.
No, I'm just saying, why does the host OS and the virtual machine monitor, why can't I let that happen? Yeah, Kevin.
Because the host OS and the guest OS could both theoretically try to use the same resource at the same time because they could both have.
Well, it's deeper than that, though. How does number 2 violate number 1? Give me an example, Gabriel.
I was going to say if you had a malicious guest.
Well, yeah, potentially malicious, right? Yeah.
Part of the reason we have this distinction between an operating system and all the other software on the system is because that should exclusively deal with the hardware and safely multiplex that with the software on the machine.
Right. I mean, remember, kernel privilege exists so the kernels can multiplex resources and divide them between different parts of the machine. As a concrete example, if I allow the guest operator, so think about memory, right? So again, I am not providing the guest OS with exclusive access to the memory on the machine, or even access to all of the memory on the machine, only to a portion. What would happen if I allowed the guest operating system to run in fully privileged mode? What could it do? It could load entries into the TLB to map anything it wants, right? It could say, hey, I know you told me to use that gigabyte over here, but that other gigabyte over there is very interesting, right? I'm very curious about what's in there, right? I'd like to use it for my own stuff. So, right, I cannot, again, this kernel privilege is what gives me access to this system resources, so I can't allow the guest to run with full privilege, right? And this in a nutshell is what's hard about writing a virtual machine monitor and providing a virtual machine abstraction, right? So the virtual machine monitor is, again, this is a computer program. Yeah, Paul.
The simulations you mentioned for performance, those are always virtualizations of, are they always run for virtualized?
No, so a simulator, that's a great question, right? So a simulator is, now yeah, this gets interesting, right? So you can measure the performance of programs running inside a virtual machine. Sometimes the virtual machine will give you access to more information about what the program is really doing than you would normally have. But when we talk about a simulator for performance analysis, we're talking always, I should say always, almost always about something that is simpler than the actual system that's being simulated. You write a simulator to, A, provide repeatability, but also to get rid of some of the ugly parts of the system that cause it to be slow or complicated or unrepeatable, right? So yeah, that's a good question. So again, so at the beginning of the semester we said the operating system is a computer program, right? It's not some sort of magical spell, right? It's just a computer program like other computer programs. It has some special responsibilities, gets to do some fun things. But now I'm telling you that there's a computer program that will allow you to run this computer program next to your other computer programs, right? And so hopefully this gets the point across, right? So we're going to talk about how. How's very interesting, right? But let's start out by talking about why we would want to do this, right? Because throughout the semester, we've been talking about operating systems, and we talked about the ways that operating systems isolate applications from each other, how they provide these nice abstractions and simplify programming and resource allocation, blah, 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 right? And at this point, hopefully you guys feel like operating systems are great, right? So why do I want something to run an operating system inside another maybe they're so great, right? That they're even better if they run on top of each other, right? It's not quite the answer. But let's just, again, I mean, operating systems are awesome, they're very cool, but just for the sake of argument, let's talk about some problems. And I've broken this into a couple of categories, right? So there are problems with operating systems related to what I'll call hardware coupling. One of those is that it's hard to run multiple operating systems on the same machine, right? Now this is, again, I put this up as geeky, right? Because this is not something that normal people do, right? I've tried to convince, recently my mom was trying to decide what computer to buy, and I really tried to convince her to get a Mac, and she said, oh, I have this Windows software I need to run. I was like, no, you could just run VirtualBox. And she's like, what? Like, she's not going to do that, right? Like a normal person isn't going to do this, right? Maybe future people will do it, but today's computer users don't typically do this. But this is potentially more problematic, right? So if I have a setup, right? And by setup, I mean the entire machine environment. It can be difficult to transfer that to another machine, right? If I take a binary piece of software, right, that you have running on some machine, and I just take that binary, just move it, right? Move it to some other machine. Sometimes it'll work. Sometimes it won't work, right? Because that binary depends on libraries. That binary has, if the instruction set is different, obviously it's not going to work, right? Clearly, right? So this can be a problem, right? I have, because the software has gotten to the point where it's complex enough that there are a lot of dependencies. And so if I want to ship, an appliance, right, a whole software environment that works out of the box, I may need to capture some of the dependencies on the operating system and other libraries, right? And this is another potential problem, right? Which is, let's say that, let's say that you set up a web server, and you realize that that web server has way too much RAM, right? Like you set it up for your brand new personal homepage, right? Because you knew you were going to get like millions of hits, right? A second. You put like a lot of RAM in there, and then it turned out that you weren't getting that many hits, right? So what do? How do you reprovision physical resources on this machine? Well, right, you can shut it down, open it up with a screwdriver, right? Pull out those, big sticks of RAM that you paid so much money for, right? And put them back into your, your file server or whatever else, right? But that's kind of gross, right? So reprovisioning the physical resources under the operating system is not always so easy when we're talking about bare metal, right? And this to some degree is where things get really fun, right? Because a lot of the cloud computing that you guys enjoy the benefits of today utilizes virtualization to avoid having to do the static resource provisioning. I don't know how much, again, you don't know how much memory that website's going to need, or that database server is going to need, or what type of machine resources. And so having to pick a static set of hardware to run that on can be a problem, right? And most of cloud computing relies on virtualization to do play all sorts of tricks and make the most out of actual physical machines, right? All right, so application isolation. So this is another problem, potential problem that operating systems have, because we've talked about the ability of operating systems to isolate applications from each other. That's one of the things that they're designed to do, right? But it turns out that this actually is, that there's less isolation between applications than we might want, right? So the first thing is operating systems actually leak quite a bit of information about the state of the system, right, in a variety of different ways, right? And there, you could probably take several lectures in a security class on all the different side channels that operating systems end up exposing that allow applications to learn things about each other, right, about the state of the system. And to some degree that operating systems have to do that. But, if I'm company X, right, and my mortal enemy is company Y, we are big competitors, and you're my service provider, and I say, you know what, I'm going to run your app on the same machine with company Y. No, you're not, right? Because it's possible that company Y is going to learn something about me I don't want to know, or be able to sort of mess with me in ways that I'm not comfortable with, right? And another problem that's quite, that we've developed some okay approaches to solving single operating systems, but can be potentially problematic, is just software conflicts with getting applications to work, right? And again, to some degree, package managers have improved this somewhat, but it's possible that applications running on the same system need different software packages to work properly, right? Or alternatively, and these last two we've already sort of talked about, applications where they require very specific hardware configurations before vendors are going to certify that they're going to provide you support on a machine, and these machine-specific configurations may conflict with other apps, right? And so if I remember, listening to a lecture by the guy who had, one of the original developers of Zen, which is kind of a neat para-virtualization technology that we'll talk about next time. And a lot of their early push for virtualization came from this, right? I mean, companies were being forced to buy an entire machine just to run their database server, because otherwise the vendor would provide support for it. All right, so now, now that we've described some of these problems with virtualization, what are the sort of the cool things that we can do, right, now that we have this technology? One is, and maybe I just like this one because I use it, you can put together an entire environment and distribute. How many people have ever used a virtual appliance that's been provided by other than mine, right? That's been, yeah, you can go online and they'll be like, oh, try out this software package. Here's a tiny little VirtualBox appliance. You boot it up, it's got everything installed, you can play around with it, you can make as much of a mess as you want, which is pretty fun, actually. If you guys have any interest in making a mess on systems, I would suggest you use virtual systems, right? Because when you're done making your mess, you just hit delete and the mess is gone, right? I've had a couple of students that I've worked with where it's like they're working on a bare metal machine and they start debugging a problem, and pretty soon they're just plugging in answers from Stack Overflow and just running them as root at the command line, and pretty soon I'm just like, just start over, just reinstall the operating system and start from scratch, because you have done so much damage at this point that there's no way to get this machine back to a workable configuration. So anyway, but if you do that in a virtual machine, it's much easier to do this, right? Virtual machines allow you to take snapshots, also a cool thing, right? Another thing we can do is we can dynamically reprovision physical machine resources, right? So I can take, and there's, every cloud computing provider on the planet is interested in how to do this properly, right? I take a bunch of big, fat machines, and I sell them to you in a bunch of little slices, right? If you've ever used EC2, you've been a part of this, right? Your little, whatever it is, micro instance. How many people have used EC2 before? Okay. So here's the thing, right? Just a little side rant. You guys are computer scientists, right? EC2, you can set up a micro instance for free, right? It costs you $0. So just go do it, right? That way when you go to an interview and someone says, have you ever used EC2? You can be like, yeah, I set up a micro instance and used it to run my really popular website, right? Whatever, it doesn't matter. But yeah, EC2 is free, so you guys should go and play around with it. The tools that Amazon provides for this sort of environment are really cool, very complicated, but also something that's worth getting to know. But if you do this, your little, micro server, which provides you a small amount of storage and very, very wimpy CPU and memory, is essentially being packed on to a big, fat, powerful machine along with a bunch of probably other micro instances by other cheapskates like yourself, right, that are all being thrown onto one machine where they can all duke it out, right? Because who cares about the performance? It's free, right? Clearly there's no SLA that's governing in this micro instance, just as slow as they can make it. And the other thing that's going on, potentially with your knowledge or without your knowledge, it's a lot easier to pick up an entire machine, just put it somewhere else, right? Move it across the country, move it to a different part of the data center, move it to another machine where its resource usage is a better fit. So this happens as well, right? I mean, this is happening all the time on the services that you're using virtualization to reprovision machines as they need to. If a machine goes down, right? Or if I need to take a machine down for maintenance, move all the virtual machines onto another one, take the machine down, replace it, move them back, I'm done, right? There's no way you can do that with physical machines. It's just not possible. So, yeah.
Isn't there like a lot of state, like the last thing you mentioned, isn't there a lot of state they have to save?
Yeah, this is a heavyweight process, right? But it's possible, right? And I have a little VMware console set up, and I manage some virtual machines where we run experiments, and I've used this feature. I mean, you have a machine, it's all set up. You need to launch another machine over there, or for example, like the ops class grader is slowing down because of all the data processing you're doing on the same host next to it. You just move it to another machine, right? But yeah, well, and also duplicating machines is also quite nice, right? So I think, if I remember correctly, I have the backend grader for this class set up so that I can create more copies as I need to, right? So in 2 weeks and 6 days, right, when it's sitting there cranking away on all of your broken assignment 3s, we can fire up another one just to shed some load, right? And they're set up so they come up, they register with the machine, and they're ready to go, right? So at least that was my intention. We'll see if it works, right? Haven't tried this for a while. But yeah, I mean, there's a fair amount of state to move around, right? And that, of course, makes the problem of dynamically reprovisioning machines to provide services pretty interesting, right? Because I can't just throw the machine onto another machine when I'm talking about stopping it potentially. You can do live migration in certain cases. There's software that allows you to move a machine without even turning it off, right? Which is pretty awesome. So it's funny how not new of an idea this is, right? So in 1974, these two computer scientists provided 3 requirements for a piece of software to be considered a virtual machine monitor, right? One was fidelity. The software I run inside the virtual machine monitor should run the same way it would on real hardware. Modulo timing, right? It's going to be probably slower. There might be some other timing differences, but it shouldn't produce different results, right? That's important, right? The second is performance, right? It might be a little bit slower, but it shouldn't be dog slow, right? And this is funny. This isn't really a requirement. It's just a hope, right? Like the performance shouldn't be terrible, otherwise no one's going to use this thing, right? So, and the way that you accomplish this, right? This is very important. We'll come back to this as we talk about the technologies for achieving virtualization, is you run as much as you can on the physical hardware, right? What's fast, the physical hardware. What's slow, potentially, is all the stuff you have to do to isolate the virtual machine from the other virtual machines that might be running on top of the same hardware, or from the host operating system, right? But the way you achieve good performance is you run as much as possible on the bare metal, right? And finally, the VMM should manage all the hardware resources that are provided to the virtual machine, right? So the virtual machine should not be able to sort of pierce the guest operating system should not be able to pierce the virtual machine, right? See memory that's not allocated to the virtual machine, interact with things, other virtual machines, stuff like that, right? So the virtual machine monitor needs to provide this isolation. So there are really, you can separate virtualization into largely 2 approaches, right? And what we're talking about here too, I want to just make a brief clarification, which is this is hardware virtualization, right? So these are approaches to virtualizing hardware. There is something else called OS virtualization, right? Which actually happens within the operating system, which can allow one operating system to look like 2 copies of the same operating system to applications that are on top of it, right? But that's not what we're talking about here. What we're talking about here is hardware virtualization. That's the usual use of the term, right? There's two ways to do this, right? So in full virtualization, the virtual machine monitor allows you to literally run an unmodified copy of the operating system that would run on real hardware. You take the binary for the operating system that would run on a real x86 device, And you can load that exact same code inside the virtual machine monitor, right? And there's problems with this, right? Because the stuff that's going to run on real hardware is going to want to do things that you don't want it to do. We'll talk about those today, right? Or on Monday. Paravirtualization, on the other hand, which is quite popular, requires some changes to the operating system, right? So early approaches to virtualization said we're not going to assume the operating system is going to make any changes on our behalf. We'll just do everything ourselves. And then paravirtualization says, you know, there's some things I can do to the operating system itself that'll make it more friendly for virtualization, right? And if I do those things, the operating system becomes a lot easier to virtualize. And essentially, these involve improving its interaction with the virtual machine monitor, right? Reducing the amount of bad things it's going to do that the virtual machine monitor needs to track and try to stop, right? So let's talk about full virtualization first. Again, the goal is run an unmodified operating system, the same thing that would run on real hardware. Probably the best known provider of these software solutions is VMware, right? VMware, you know, pioneered a lot of the technology that's used in this area. So again, let's go back to asking ourselves, why is this hard? Why would it be hard to run the unmodified operating system inside a virtual machine? What are some problems I'm going to need to deal with? Yeah.
You're going to have to catch it every time it tries to access things it's not supposed to have.
Yeah, so the operating system is going to try to execute privileged instructions, right? It's going to think, right? Again, and it's supposed to think, right? It's going to think that I am the operating system, right? You know, hear me roar, right? When I tell you to change the TOB, thou shalt do it, right? You know, when I, you know, like, and it's going to, I want to manipulate this register on the processor that can only be modified in privilege mode. And again, if I allow the guest OS to run in privilege mode, I'm toast, right? I can't do it, period, right? Not even for one or two instructions. It's not safe, right? And actually, yeah, this gets even, this whole thing starts to seem like those Russian egg dolls, right? So it gets very, so the first thing is, if an application, remember, I'm running on bare metal, right? I'm trying to run things as much as possible that runs inside the virtual machine on the real hardware, right? So let's say I have an application running. Now the application is safe to run, right? Because it doesn't run with privilege mode. But what do I need to do when it traps? Let's say an application running inside the guest operating system performs a system call. Who needs to handle that system call? Yeah. The guest operating system, right? But where is that system call going to generally go by default? Into the host operating system call handler, right? It just does a system call. It jumps to the host operating system and starts executing instructions, right? So somehow I've got to get it back into the guest operating system and allow the guest operating system to handle it, right? So that's one problem. And then, of course, the guest operating system is going to try to execute these privileged instructions, right? So let's try the following, right? Simplest possible approach. Let's just take the guest operating system and so we can't do this, right? Let's just run it with user privileges, right? So when it raises the privilege mode, or when it thinks it's raising the privilege mode, I'll just remove those instructions or ignore it, right? Or, for example, so normally when the application traps, the trap raises the privilege mode and starts executing inside the guest operating system. But I'm actually going to raise the privilege mode and start running in the host operating system. And now what I can do is, by the time I revector the trap into the guest operating system, I can lower the privilege level, right? So what would have normally raised the privilege level, the trap does raise it when it's running in the host OS, but by the time I get it to the guest OS, I've dropped the privilege level. So the guest OS thinks, naturally, hey, I'm in the trap handler. I've got kernel privilege. This is cool. But it doesn't, right? So I took it away. But what will happen if I do this? Right? It's just, the guest operating system is just a series of instructions. What's going to happen?
So can we use the user privilege as the kernel privilege in the virtual?
Well, so again, that's what we're going to try, right? What we're going to try to do is run the guest operating system with user privileges. No privilege for you, right? You're the guest. But what happens, right? Guest operating system starts running. It doesn't know that it's not running with kernel privilege. But what will it eventually do? Yeah?
Should I cause an exception so they can try and execute instructions kernel privilege only or user mode?
Yeah, I mean, eventually it's going to try to execute something that needs privilege, right? Now the important thing, and the critical thing for making this work, the only reason this does work, is that a lot of what the host oh man, this part of the class requires a lot of concentration on my part. There's like 3 operating systems flying around here. A lot of what the guest operating system is going to try to do doesn't require privilege, right? A lot of it, the privilege level is raised, but a lot of it's just like standard instructions, right, that could be executed by user processes, right? And then there's this one instruction that I execute that needs kernel privilege, and now I'm in trouble, right? So what we do, the CPU is going to trap, right? Because, and this is a nice feature here, right? Because there's a privilege violation, right? This is the same thing that would happen if a user application tried to execute a privileged instruction, right? That trap has to get handled by the virtual machine monitor. So when you guys installed VirtualBox, Windows probably blanked out and like made you sort of click on some stuff, right? So just to be clear, this requires cooperation by the host operating system, right? There's no way to do this without installing special drivers and making modifications to the host operating system to get this to work, right? Maybe there is a way to do it, but I've never heard of it, right? I don't think you can run an unprivileged, like a VMM that doesn't require the cooperation of the host, right? Because again, normally, what the host would see, it would say, hey, this is an application. Because again, to the host, what does this look like? It looks like an application called VirtualBox, right? It doesn't know what VirtualBox is doing, right? But VirtualBox just tried to execute a privileged instruction. So what would I normally do? Kill it, right? But I can't do that, right? I need to get, in certain cases, sometimes I might need to kill it, right? But in certain cases, I need to vector those exceptions back into the virtual machine monitor and allow the virtual machine monitor to handle them, right? So now, assuming the guest operating system is doing something legitimate, hello, where did this come from? What actually has to happen is the virtual machine monitor has to adjust the state of the virtual machine, right? Remember, I'm simulating this alternate piece of hardware, right? So for example, the guest operating system might have tried to write to some register on the CPU it's not allowed to use. It's supposed to have some effect on the underlying physical hardware. I need to make sure that the virtual machine reflects those changes, right? Where this is good stuff to talk about this during the time of the semester, because this really is we'll sort of, if you guys think through this and think through some examples of how this works, this will really make sure you understand these sorts of concepts, right? Because it's very interesting. Paging, I don't think I do anything about paging yet. Maybe we'll have to go through it. Paging in these systems is terrible, right? You have these shadow page tables. It's like, yeah, I mean, it confuses me even just thinking about it, right? So now, here's the thing, right? So if I can handle an instruction this way, right? This is called trap and emulate, right? Then this instruction is known as being classically virtualizable, right? And this approach, again, is called trap and emulate, right? I allow the instruction to generate a trap, right? Which is what I hoped happened because it required privileged mode. I vector the trap into the virtual machine monitor. I adjust the state of the virtual machine, and I'm good. I just let the operating system, the guest operating system, continue to execute. Sadness. Well, okay, let's go through this, right? We'll get to the sadness part in a minute. So what does the VMM do with traps that occur within the virtual machine? So if the trap is caused by the application, right, that trap needs to get revectored into the guest operating system. And if the guest operating system caused the trap, then I need to handle that in some way within the virtual machine itself, right? So this is now doable, right? And like I said before, these approaches require operating system support because I need to revector traps that would normally be handled by the host operating system and exceptions that would normally kill the process, right? The nice thing about this approach is that it allows the guest and the applications running inside the guest operating system, most of the time they're just using the machine the way they normally would, right? Again, we're running as much as we can, just using the same CPU, running standard user mode instructions, right? So now let's go through the process of making a system call, right? Syscall, I trap into the host OS, vector this into the virtual machine, right? The virtual machine inspects the trap, realizes this is a system call, now starts executing the guest operating system trap handler, right? Which will eventually handle the trap. Now when it's done, it calls RFE, right? Turns out RFE is a privileged instruction, right? So this traps back to the host operating system, which vectors the trap back into the virtual machine, which sees what's happening, and then continues executing inside the process that executed the system call, right? I wish I had a thing for this. So it's like boom, 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 right? Simple. Does this make sense to people? Let's just pause here to make sure that. So the trap gets, the system call is handled by the host operating system. Because I have because it's cooperating with me, that gets vectored into the virtual machine monitor. The virtual machine monitor sees that the system call, starts executing the guest operating system call handler. That just runs normally. When it finishes doing whatever it needed to do, if it was a read. Now, there might be some other exceptions that it handles along the way that I need to deal with. But when it finishes handling this read or write or whatever, it calls RFE. That traps back to the host operating system, passes it to the virtual machine monitor. The virtual machine monitor sees that the guest operating system is returning from the exception, jumps back to the process that generated the system call, right? So there's some overhead here, yeah.
The privileged instruction, is it, the privileged instruction that is generated by the guest OS, is it actually then executed on the processor, or is it emulated?
No, it's executed, yeah. So here's the trick, because I think we're going to get to the sad part now. Anything is as long as the instruction that should be executed in privileged mode generates an exception, then I can do this, right? I run it without privilege. So essentially what I can do is I can just allow the guest operating system to run without privilege, right? Whenever it does something that needs the virtual machine monitor's attention, I'll get it because it traps, right? So essentially it allows me to isolate the exact instructions that the virtual machine monitor needs to handle, right? Because those are the ones that generate an exception because they needed privilege and the guest operating system didn't have it, right? The only trick here is distinguishing between traps that are generated by applications and traps that are generated by the kernel, right? Because those paths are a little bit different, right? Yeah, Tom.
So is the VMM kind of like a kernel
I
also?
wouldn't call it a kernel, right? The VMM is just, the VMM, well, the VMM does a lot of things, right? But here the VMM is just sort of directing traffic, right? It's figuring out which code path should this go down inside the virtual machine.
So when you virtualize a OS, there's no kernel inside that virtual environment?
No, remember, we're not virtualizing an operating system. What are we virtualizing? Hardware. The operating system is a real program that's running inside the virtual machine. The machine is hardware, right? So that's important, yeah.
So can, like, through the use of the VMM, can the guest OS, like, make a modification to the TLB on host?
Yeah, so yeah, that gets into this whole shadow page tables thing. I'm trying to think
Does
of.
it have its own table then? Or how would it know, like, which entries are its own and not the host?
Yeah, so this gets, well, okay, so here's the thing. If, if I had a software managed TLB, I actually think this would be easier, right? Because what the VMM and the host OS can do is just verify. So what I want, remember, I cannot trap every memory instruction, right? Because that would be terrible, right? Your virtual machine would still be loading, right? Your kernel for the semester. So instead, I want to use the TLB. I want to use the TLB normally. What I have to do is I have to just make sure that the guest operating system doesn't load any translations into the TLB that allow it to see memory it's not supposed to be able to see, right? that can be done by the VMM in conjunction with the host operating system, right? Where this gets even more complicated is on x86, because x86 doesn't have a software managed TLB. So it has page tables, right? And the hardware will search the page tables automatically, right? Anyway, like I can't even explain this without sitting down and looking at it. And maybe we'll go over it next week, because it's pretty interesting. But there's several levels of indirection, right, that are required to safely allow x86 virtual machines to use memory. But yeah, if I had a software managed TLB, all the host would have to do is make sure that those entries are OK. And then when the VMM is switched out, I can either clear the TLB, which is fine, or I can save its entries and reload them the next time, right? The idea is that the VMM has its own section of memory, right? And that chunk of memory, it's allowed to provide access to the operating system running inside the virtual machine, right? It's a good question. David?
This is a random question, but is it possible to install a virtual machine in a virtual machine?
I don't know. I've never tried it. Someone should try it. I mean, it's possible? Yeah. I wonder how bad performance gets, right? OK, by next time, there'll be a prize for the person who gets the largest nesting of virtual machines. 8 deep. I've got Ubuntu running inside Ubuntu running inside Ubuntu. It's super fast. It's like once you get to 7, it gets faster, right? Yeah. Oh, actually, you know what? I have a slide on this. Wow. OK, so let's go through this again, right? TLB fault, right? Trap to the host OS. Hand the trap to the VMM. Looks to see that it was generated by an application, passes control to the guest OS. The guest OS has to handle the TLB fault. What's going to happen when the guest OS tries to load an entry into the TLB? Exception, right? Trap back to the host operating system. Trap gets handled to the VMM. The VMM has to look at the trap, see that it was generated by the guest, because if it's generated by an application, I have a problem, right? And then it has to adjust the state of the virtual machine appropriately. What it would actually do here is allow, if the guest operating system is loading a translation to memory that's been allocated to the virtual machine, then this is OK, right? If not, then this is not OK. This is another place where we're exploiting the fact that the VMM has to cooperate with the host operating system, right? Because otherwise, I wouldn't know, right? Because the VMM doesn't have a view of physical memory. It only has a view of virtual, right? But I need to know that the physical address that the guest operating system is trying to translate is actually allocated to my virtual machine, right? So that's another key piece of information the VMM has to use the host OS to figure out, right? So again, what we're virtualizing here is the hardware interface. I don't want to do this. Let me just sort of see through this, right? So the interface, but what's interesting here is the interface here is all the instructions. Like essentially, I need to virtualize the instruction set, right? And what's particularly important are the instructions that modify the state of the machine. Normally, those are instructions that only the kernel is allowed to execute, and so they require some form of privilege, right? For example, adjusting the TLB involves modifying the state of the machine, right? Here, I'm going to intercept or rewrite unsafe instructions, and I allow as many safe instructions as possible. Essentially, I'm going to trap and emulate these instructions. I allow the safe instructions to run on bare metal, right? All right, so yeah, here we go. So this gets to the sadness, right? The sadness was I had this great property, which is that if the instructions that require a kernel privilege trap properly, then I can emulate them, right? The problem is that x86 doesn't work like this, right? There are instructions on x86 that essentially you can run in either user or kernel mode, and they just behave slightly differently. Yeah. I don't know if that's a feature or a bug, right? It doesn't matter. From our perspective, it's a bug, right? Because now I've got this terrible problem, which is that I was relying on the fact that these kernel privileged instructions trap so I could emulate them. Now they don't trap. They just don't do the right thing, right? And of course, x86, I mean, whatever. We don't need to virtualize x86. It's not an important architecture, right? Nobody uses it anymore. It's like, yeah, exactly. So the problem was that, you could be like, oh, well, let's virtualize ARM, right? Yeah, great, no one's gonna use it. So what VMware did to work around this problem, which is really interesting, was they performed, it's almost like JIT, right? But they performed on-demand binary translation. This is what you have to do. There's really no other way to do this. So what they would have to do is they'd have to look down the code path that the kernel, that the guest operating system was using. And they would rewrite non-virtualizable series of instructions, right? So if a particular block of instructions included one of these instructions that was not classically virtualizable, I have to rewrite it to trap, basically. I have to force it to trap and then rewrite it with the instructions that generate the right behavior, right? And in order to improve performance, so I'm not doing this constantly, VMware had these clever approaches where they would cache translations they had made previously, kernel code's not changing, right, et cetera, right? So this is what we did to get around this problem, right? So yes, and I've glossed over, for x86 stuff today, I've glossed over all sorts of things, right? Privilege rings. Anyone remember privilege rings? We talked about them a long time ago. Yeah, those get used now, particularly with para-virtualization. Primary and shadow page tables, the whole universe there. Go look these up, it's very cool. Yeah, now that virtualization has become more popular, architectures, including x86, have developed better support for it in future versions of their ISA. So they're working on getting rid of those non-virtualizable instructions to make this more simple. There's a lot of cool stuff out there. VMware has great resources for learning about these things, right? Memory management between the host and the OS, very interesting, right? How do I get the guest operating system to feel like it's under memory pressure? It's pretty cool. So next time, we'll look at the other approach to virtualization, which requires modifying the guest operating system.